In this tutorial we will learn how to simulate cavitation in internal flows because of pressure drop. For this purpose, we have simulated this test case from ANSYS verification manual. As you can see, our results matched with experimental value as well as the CFD values provided by ANSYS with sufficient accuracy. Let's learn. Open Design Modeler and draw a sketch in XY plane. As the flow will be symmetrical around the central axis, we will model this geometry in 2D with axis symmetry to reduce computation time. Draw straight lines using auto constraints. H means the line is constrained to be horizontal and V is for vertical constraint. Give all the dimensions. Just make sure that the central axis aligns with x-axis in Design Modeler. Go to Concepts and make a surface from this sketch. Change it to Fluid and close Modeler. Now we are in meshing. Give a face sizing of 0.2 mm. Give inflation to the outside walls. We are using a first layer thickness of 10 microns with 20 total layers. We have obtained a nicely structured quad mesh with fine elements near the wall. We can later refine it further for mesh independence. Now, we will create name selections for boundary conditions. Click on the edge and press N to create a named selection. You can right-click and select the option Create Named Selection. We need an inlet, axis, and outlet. Close meshing. Open Setup from the system. As this is a multi-phase problem, select Double Precision and Parallel Processing. Specify the number of cores for simulation. We have specified 4 cores. The model was successfully read by Fluent. We will select the pressure base solver as it is an incompressible flow. Change the 2D space to axis symmetric. Turn on multi-phase modeling from Models tree. Select Mixture Model. Retain the default settings. Before we can assign phases, we need to define materials. Right-click on Fluid and select New. Select Fluent Database. Select Water Liquid and Water Vapor from the database and click on Copy. Double-click on water vapor and change its properties according to operating pressure and temperature. Click on Change. Values for liquid water are pretty much same. Now, go back to multi-phase models and click on Phases. Select liquid water as primary and water vapor as secondary phase. Now, we will define models for interaction between the liquid and vapor phases. There are multiple drag models available in ANSYS Fluent. Schiller-Naumann is one of the most commonly used models as it is acceptable for general fluid-fluid pairs. You can read more about them in ANSYS Theory Guide. Next up is slip velocity model. There is only one model available for slip velocity calculations. Go to Mass tab and create a mass transfer mechanism from phase 1 to phase 2. Select cavitation from the options. There are two models available here. Both models are highly robust and converge easily. We have selected Swart-Gerber model with default values. Set the vaporization pressure according to your problem. Specify the surface tension. Inclusion of surface tension, however, may or may not have significant impact on your results depending on the Reynolds number. Multiphase modeling is complete. Select the turbulence model. We have selected RNGK epsilon with standard wall functions. Now set the boundary conditions. The axis has already been set because of its name. Specify the inlet and outlet boundary conditions. We have values of pressure available at both ends, so we have chosen pressure inlet and pressure outlet boundary conditions. Check conditions for both phases at the boundary. Make sure that the phase 2 has 0 volume fraction at the inlet. No special considerations of solution methods are required for this problem, so just use default methods. We are using small values of under-relaxation factors for pressure and momentum. This helps stabilize the solution, however more iterations are needed for convergence. Now, the most important part. Experimental and CFD results provided by ANSYS are in the form of discharge coefficient, which is the ratio of actual mass flow rate to theoretical. We have to define an expression for it. First, go to Report Definitions and click on Mass Flow Rate in Surface Reports. Create a report for mass flow. By report plot, it will draw a graph at each iteration. Print to console means reporting its numerical value here at each iteration. Click OK. Right-click on Report Definitions and create a new expression. Here we can see the report we have already created. Select this report and type the whole expression from the on-screen buttons. The area in this expression is actually the area of smallest section. Its area into square root of 2 times density into total pressure difference. Close the brackets and give it an appropriate name. Everything is ready now. There are no special considerations for initial conditions as well, but I found initializing from outlet conditions to be more stable in this problem. Give a large number of iterations and run the simulation. We have stopped the solution after some iterations just to check if it is working as expected. Draw the contours of volume fraction. Click on Filled option, otherwise it'll only color nodes. Here we can see that cavitation has started just as expected. So, The solution is running just fine. Continue the solution for a converged solution. Here we have a converged solution with mass flow and discharge coefficient values stabilized over numerous iterations. As you can see that we have obtained a discharged coefficient of 0.628 against the experimental value of 0.62. So we have a 98.7% accuracy. Discharge coefficient calculated by ANSYS is 0.631 with a 98.2% accuracy. The values have sufficient accuracy to consider the model as validated. This is it for now. If you have any questions or suggestions, please feel free to tell us in the comments. Thank you for watching.